Now, as applications, we'll talk about two results proved using a variational principle. So it is a major challenge to compute the Hausdorff dimension of the set of the set of the singular matrices of n by n. The first breakthrough was made by Chang in 2011. He proved that the Hausdorff dimension of this is 4 divided by 3. And later in 2016, they proved the Hausdorff dimension of the singular matrix or singular vectors, rather, is m squared divided by m plus 1. And later, Kadyrov, Kleinbach, Lindenstrauss, and Margulis proved that the upper bound for the singular matrices, m by n matrices, is given by this delta sub mn. And Das, Fisherman, Simons, and Urbanski proved recently the upper bound of this is actually sharp. Actually, they used a completely new method and to prove this equality. Specifically, they proved that both the Hausdorff and the packing dimension of the set of m by n singular matrices is equal to this quantity. The second application is a reproof of Schmitt's conjecture on the successive minima functions. So Schmitt's conjecture states that for all integer k between 2 and m, there always exists a m by 1 matrix, or rather vector, such that the k minus 1 minimum of this lattice tends to 0 as t goes to infinity, while the k plus 1 minimum of this lattice will tend to infinity as t goes to infinity. So this conjecture was first proved by Shevetin in 2012. I think he actually constructed such a vector satisfying this. To introduce Das et al. The recent results on the reproof of this conjecture, let us denote. They actually prove this for general m by n matrix A. M by n matrix A is k singular for k greater than 0 and less than or equal to m plus n minus 1 if this convergence property is satisfied. And their proof is non-constructive in the sense that they actually compute a lower bound for the Hausdorff dimension of the set of matrices satisfying this. The set of matrices satisfying this has a Hausdorff dimension at least the maximum of the value of those two functions. Now in this section 4, we're going to talk about some directions to further research. The first problem is to prove that the lower bound in the theorem is actually sharp. So remember, they proved that the Hausdorff the dimension of set of matrices satisfying this condition, this convergence condition, has a Hausdorff dimension at least this thing. In particular, this something greater than 0. And now a natural question to ask is that whether this lower bound is actually sharp. Yeah, this is our first question. The second question is about how is the Hausdorff and packing dimension actually depend on epsilon. Remember in the definition we said for arbitrary epsilon, small epsilon, blah, blah, blah. But here we are more interested in the dependence of this Hausdorff dimension on this epsilon. And we can even give this definition. An n matrix A is called epsilon dirichlet provable if for sufficient large Q, there is integer vectors PQ such that the norm of AQ minus P is bounded by this thing. And ask about the Hausdorff dimension for the epsilon dirichlet provable singular matrices. This is the second question. The third question is about replacing the GT flow they studied by some new flow. Remember previously, we have e to the t divided by m, e to the t divided by m, and here it will be e to the negative t divided by n through e to the negative t divided by n, where those a1 through am, b1 are all 1 over m, and b1 through bn are all 1 over n. Now we replace them by some arbitrary number, but still make sure they are in a special linear group. So with this more arbitrary parameters, can we still study the Hausdorff dimension? And this is a question addressed by Liao Shi and Solon and Tamam for the case m equal to 2 and n equal to 1. The next question is about, so previously we were only interested in a singular matrix A, but now we try to extend the definition to the singular pair. So we have a m by n matrix A and a vector x, and we consider this pair. This pair is called singular if there for all epsilon greater than 0, there's a q such that for all q greater than q epsilon, there are integers p and q, integer vectors p and q such that we have this inequality, and we put an x here. Now it will be interesting to study this inhomogeneous approximation. We may want to fix one of them and let the other vary, and we try to find the Hausdorff dimension, whether it is a precise dimension or a upper bound or lower bound. And when m and n are both equal to 1, which means in the one-dimensional case, this has been investigated by Lim, Kim, and Liao. And it would be interesting to modify the methods given in the paper by the Das et al. Namely, if we can find some new version of a variational principle and replace all the framework in that setting. So hopefully that will open some door to this question. Finally, I would like to talk about some related topics, which has more focus on the homogeneous dynamics. So those results I'm going to present are quite recent. So for the settings, let G be a connected Lie group and gamma be the lattice in G, and mu be a G invariant probability measure on this quotient homogeneous space. Now we consider a sub-semi group F of G and a non-empty open subset of U, and define the following set. This set says this orbit of X under this sub-semi group always avoid this open subset. So, and we consider all such possible points, all the possible points whose orbit and F avoids U. If we further assume F acts ergodically on this homogeneous space, then we can prove that this set is actually mu null. So now we have a conjecture. This is a question I think asked by the fields medalist Amir Zahani through some private communication with Kleinbach. If F containing G is a subsemigroup and use an open subset of X, then either E of FU, this subset, has positive measure, or its dimension is strictly less than the dimension for X. And for the case of the special linear group and the diagonal flows, Kleinbach and Mirzadeh obtained the following result. So if G is a special linear group and gamma is special linear groups over integers, and for parameter a greater than 0, we consider the following subsemigroup, and they prove the dimension drop conjecture holds. Yeah, it's quite recent. And actually what they proved is a quite quantitative version of this. And I'll be happy to explain to this in further if I have time to use the tablet writing instead of the Beamer. The next quite related topic is about so suppose we have an arbitrary one parameter subgroup action on a finite volume homogeneous space. On the other hand, for an arbitrary one parameter subgroup, action on a finite volume homogeneous space, Guo and Shi proved recently a version of a dimension drop conjecture for the set of points with divergent trajectories. And the definition is given below. G is a connected Lie group, gamma lattice, and we consider the semigroup parameterized by the non-negative numbers. For the point X in the homogeneous space, we say the trajectory of X under F plus is divergent. And we denote the set of such points by if F sub T X leaves any fixed complex subset of G mod gamma, provided T is sufficiently large. And there's also a notion called the divergence on average. And the set of such points is denoted by D without prime. If for any characteristic function 1 over k, so if you consider this averaging integral, so eventually it becomes 0. And you can see the divergence implies the divergence in average. And Guo and Shi proved that if gamma is a lattice of the connected Lie group, and let F be a one parameter subgroup of G, then the Hausdorff dimension of the set of the points divergent on average is strictly less than the Hausdorff dimension of G mod gamma. And this answers a previous conjecture by Chang in 2011, where he conjectured this for the D prime. Okay, so this will be the end of my presentation.